Hi there. In this video, I'd like to describe several ideas about circles. The first relates to central angles. If we have an angle with a vertex at the center of a circle, let's say a right angle, then the arc that is subtended by that angle is also going to be 90 degrees. Now, if there's an angle with a vertex on the edge of a circle, it's called an inscribed angle, and the measure of the subtended arc is going to be twice the measure of the angle. So if this is 40 degrees, the arc is going to be 80 degrees. This leads to one of my favorite facts about circles. If there's an inscribed angle that is a right angle, the other 2 points are on opposite sides of the circle, and a diameter connects them. Now, these 2 ideas can be generalized for any 2 lines that cross a circle. The measure of this angle is going to be the average of this arc and this arc. So if this is called A and this is called B, and we call this X, we get the relationship that X equals 1/2 A plus B. In a related way, if we have a circle that's crossed by 2 lines that meet outside of the circle, then the angle formed here is going to be half the difference of these 2 arcs. So if we call this C and D, and let me call this Y, we get that Y equals 1/2 C minus D. Now I'd like to mention a couple other ideas that relate to circles and segments. If we have 2 chords in a circle that are the same length, the arcs that they subtend are also going to be the same size. And in a similar way, if there is a point off of a circle and we connect tangent lines from that point to the circle, we know that the distance from that point to the point of tangency is going to be the same on both sides of the circle. So for example, if this is 10 feet, then this would also have to be 10 feet. Finally, relating to tangents, if I add the line that goes to the center of the circle, the radius from the center to that point of tangency, it will form a right triangle here. And let me mention one last thing related to chords. 2 chords that are the same length, we know, are also going to be the same distance from the center of the circle. So drawing a line that forms a perpendicular with that chord, those 2 lines are going to have to be the same size. And incidentally, the place where they intersect is going to be the midpoint of the chord. So these turn out to be 6 key ideas about circles. These ideas can be extended to solve lots of different types of problems. But first, let me talk about the 4 ideas related to angles. These are all connected to each other. And so I just wanted to highlight a little bit the connection. This idea here, the difference of the arcs relating to an angle outside of the circle, if you imagine, this point could be pushed onto the circle and then that arc would disappear, and that would put us in the situation that we have up above, where the larger arc is just double the size of the angle. So this relates very much to the idea of an inscribed angle. And this idea of averaging the angles when chords cross inside of a circle, it relates to the idea of a central angle. Because if we extend these two sides across the center of the circle, this arc is going to end up equaling this arc. So they would both be 90 degrees. And relating the two ideas now, right, if I take this 90 plus that 90 and divide by 2, I end up with 90 degrees, which is what we have as a central angle. And so that relates to the fact that wherever two chords cross in a circle, I can take the arcs subtended by those chords and average them together to find the angle inside the circle. But let me note that when we talk about this, I mean this angle relates to these two arcs. We could take this angle and relate it to the other two arcs. So this angle would relate to these two arcs. Now let's look quickly at a couple of extensions that could come up in some problems you might see. First, if we have an inscribed quadrilateral, notice that this angle and this angle are both inscribed angles, and the first one relates to this arc, and the second angle relates to this arc, which makes up the whole circle. So since we divide by 2 to get from the arc measure to the angle measure, we know that opposite angles, these two angles opposite each other in the quadrilateral, have to add up to 180 degrees. They have to be supplementary. Another quadrilateral figure could be formed by crossing chords in the middle of the four-sided figure. And then notice, for example, this arc relates to both of these angles, so those two angles have to be the same size. This idea about tangents can be extended to the idea of an inscribed circle, or I could say a circumscribed polygon. So if I have a polygon, a triangle, or a four-sided polygon, or whatever number of sides, then we can think of the sides of the polygon as representing tangent lines, or at least parts of tangent lines. And so just like in this figure, each of those parts would have to be congruent. So these two parts of the sides of the polygon would have to be the same length, and similarly these two would be the same length, and these two. So the distances from the point of tangency to the corners of the polygon very much relates to the perimeter of the polygon. Again, tangents relating to a circle, but now let's think about how that is an extension of this idea. The larger arc minus the smaller arc are going to have a difference that equals half of this angle, but the larger arc and the smaller arc, they also add up to the whole circle. So if I call this A, B, and C, I know that A minus B has to equal 2 times C, but I also know that A plus B adds up to the full circle, so it has to add up to 360 degrees. Finally, we can relate the distance around part of the circle to the central angle that corresponds to the endpoints of that arc. So this is called the arc length. And for example, let's say this angle is 160 degrees, and that we know the radius is 7 inches. So then the full distance around the circle is given by the formula 2 pi r. The circumference is given by 2 pi r, and that corresponds to 360 degrees, the full number of degrees around a circle. So if I want to know the distance for just part of that arc, just part of the circle, rather than the whole circumference, if I just want it for this part, then I can multiply by the measure of that central angle, which equals the measure of the arc, the angle measure of the arc. So if we multiply 2 pi r divided by 360, if we multiply that by 160, that'll give us the distance of this arc, the length of that arc. So in this case, the arc length is going to be approximately 19.55 inches. I hope you enjoyed the video. Thanks for watching.